Hello, so we're going to look at this problem today, 1.37 from Sipser, which is the language of all binary numbers that are multiples of a set number n here. So we figure out what the value of n is, and then we look at all binary numbers that are a multiple of it. So, and for each one of them, we have to show that it's regular, meaning that there's a DFA for it. So let's see. So let's look at C1. So C1 is all of the binary numbers that are a multiple of 1. Well, that's literally every binary number in existence. So that is 0, 1 star, which is clearly regular. So C2 is essentially all even numbers for that reason. And we know that all even numbers in binary end in a 0. So this is the same thing as saying all strings in 0, 1 star that end in 0. Which is the same thing as saying 0, 1 star 0. So those two are easy, but C3 is where it gets a little interesting because, so let's look at some strings that are in C3. So anything with 0 in it is just all zeros because it's a multiple of 3. Well, then let's look at 3. Well, that's 1, 1 in binary. And let's see, so 6 would be, let's see, so that would be 1, 1, 0. And then, so that'd be 6. 9 would be 1, 0, 0, 1. And we can keep going on like this. So there's not really any distinguishable pattern here. So we saw like C1, C2, it seemed like we had 0, 1 star with something after it. But C3, there's not really that kind of pattern here. So let's actually think about this for a second though. So how does a DFA read strings? So if we have a string W, which is W1, W2, W3, up to Wn, for example, let's say that's in 0, 1 star, well, the way that the DFA reads a string, of course, is from left to right. So it reads one character at a time. So, and of course the DFA doesn't actually know when the string is finished until it actually finishes. So let's see, so what can we do about that? Well, let's look at a partial string. So W1, W2, W3 up to WI, for example. So WI is somewhere in the middle of the string, and then the rest of the string. So let's actually look at the string up to that point. Well, the DFA, if the string happened to end there, has to make a determination about whether W1 through WI is a multiple of n. Well, I guess I shouldn't have used n here, but you get the point. Whether W1 through WI is a multiple of the number that we're considering. So we can actually think about, well, if it's not a multiple of the number, well, what else could it be? So let's actually look at the 3 example and then try to make a DFA for it. And then we can try to generalize from there. So we have to have a start state. I'm going to assume that we can have leading zeros. So let's see. So if we, and we're also going to consider that the empty string represents 0. So for that reason, I need to make the start state final too, because if we don't read any characters, that represents 0, which is a multiple of every number. Okay, so then if we read zeros here, then let's see. Then we should continue to stay in the same state, because if we keep reading zeros, then it's the thing that we have read so far still represents 0. The W1 through WI string, what we've read so far, is just all zeros at this point. But if we read a 1, then we can't stay in the same state anymore because we could, for example, have the string 0, 1, 0, which is not a multiple of 3 because it's 2. So we need to go to another state here. Let's call it Q1. And then let's see. So let's look at that string 0, 1, 0. Then we can go to Q1, and there are going to be transitions on 0 and 1, and we have to decide what's going to happen. So let's look at 0, 1, 0. And so this is the string that we've read so far, and either we can read a 0 or a 1 after it. So if we read a 0 after it, then that is going to give us the number 4, because 1, 0, 0 is 4. And if we read 1, we get a 5, because 1, 0, 1 is 5. And neither of those is a multiple of 3, obviously. So let's see. What could we do here? So let's do an example where it would cause it to be a multiple of 3, and one where it's not a multiple of 3. And that one is 0, 1, 1. So 0, 1, 1 is, of course, 3 in binary. So that for that reason, the from Q0 reading a 1, then a 1 from Q1, that has to be, so this has to be in a final state somewhere because it's reading 3. So what could we do with that? Well, if we read a 0 and then a 1, the 0 says 1, 1, 0, that's a 6, and then 1, 1, 1, that's 7. So we can actually see something interesting here, that if we read a 0 after some prefix string like 0, 1, 1, then that's going to multiply the number by 2. And we can actually see this in general. So if I have a string w1 up to wi, and then I read, maybe I shouldn't put a line there, then I read a 0, then this is literally just left shifting the number 1 place, for those of you who know what that is. But basically, we're multiplying the number itself by 2, because we're in base 2 here. And if we, so this is multiply by 2. And then w1, w2 up to wi1, we can see is the same thing, but we add 1 afterward. So multiply by 2 and add 1 to the result. So what are we gonna do here? Well, let's think about this formulation of the problem. So instead of thinking like building states as we go, then what are the possible things that could happen? Well, it either is a multiple or it isn't. But we can see if we look at like 1, 0, 0, 0, which is 8, we can see that 6 is a multiple of 3, but then 7 and 8 are not multiples of 3. And then when we go to 9, 10, 11, etc., 9 is a multiple of 3, 10 isn't, and 11 isn't. So we kind of have this behavior of something that is a multiple of 3, then not, and then it starts over again. So for the DFA we have here, because there are only really 3 possibilities, so like 3, 6, 9 for the multiples, and then the 2 in between for when it's not a multiple, I'm going to have 3 states because there are only 3 possibilities here with respect to being a multiple of 3. So let's see. So Q0, I'm going to think of as all the numbers that are a multiple of 3. 1 is the one right after it, and 2 is the one after that. So let's think about what Q1 would do on 0. So Q1 says that we're going to multiply the thing by 2. So if you think about it for a second, then that corresponds to, let's see, so what are we going to do here? So let's look at 4, for example. So 4 was, if we So 3 was a multiple of 3, obviously. 4 is the one right after it. So we're at Q1 right now, if we have read a 4. Not in the DFA that we had, but just in our idea. So Q1 is where we are after reading 4. Well, if we look at 8, 8 is the second place. So 6 is a multiple of 3, 7 isn't, 8 isn't. So Q2 is where Q1 should go on input 0. And then for 1 from Q1, it's the next place in line. So wherever the 0 takes us, the 1 takes us to the next place. So the 1 takes us there. Okay, so let's do Q2. So for that reason, let's look at 5. So that's 1, 0, 1. And 10, which is 2 times that number, is 1, 0, 1, 0. And 1, 0, 1, 1 is 11. So Q2 on 0, well, if we're at 5 right now, that's the second number after a multiple of 3. Well, if we read a 0, the 10 is the first number after a multiple of 3. So in fact, the 0 comes back to Q1. And then Q2 on input 1, well, if we look at 5, it's the second place after a multiple. 11 is also the second place after a multiple. And you can argue that this is actually how it's supposed to go. In general, you can argue that is how it works in general. So what we're really doing here is we're doing a modular arithmetic. So what we're really I cannot spell at 5 a.m. Arithmetic. So what is it that we're doing? So here we're actually not considering just like what's the first place after a multiple of 3, it's second, whatever. What we're doing here is looking at all of the remainders with the respect to the number that we're considering, which is 3 in this case. So it could either be remainder of 0 if we divide by 3, a remainder of 1 if we divide by 3, or a remainder of 2 if we divide by 3. So let's actually do another example, C5. So all multiples of 5. So using that same idea, well, it either could be a multiple of 5, which is a remainder of 0, remainder of 1, remainder of 2, remainder of 3, or remainder of 4. So I'm going to have then 5 states. Q0 is going to be the start state again. Q1, Q2, Q3, Q4. So let's see. So Q0 is, again, going to be the place where we have multiples. So Q0 is going to, again, be the only start state. So let's look at this. So if we take something that is a multiple of 5 and put a 0 on it, well, remember that adding a 0 is multiplying the number by 2. But if it's already a multiple of 5, multiplying by 2 is not going to change that. So this, I shouldn't have done that. So this should self-loop on 0, and then it should go over to Q1 on 1. So always figure out the 0 transition first, and then the 1 transition is the next one in the line. So let's do Q1. So if it's a remainder of 1, then if you think about it for a second, if we read a 0 multiplying by 2, a remainder of 1 turns into a remainder of 2. And we kind of saw that up here. When we had like a 4, which was a remainder of 1, multiplying by 2 gets us 8, which is a remainder of 2. So it works exactly the same way here. So remainder of 1, reading a 0 goes to Q2. And then, of course, the 1 is the next one in the line. For Q2, a remainder of 2, reading a 0, multiplies the remainder by 2. So 2 times 2 is 4. So that comes over to here on 0. The Q2 goes to Q0 on 1, because it's the next one in the line. Q3, well, a remainder of 3 times 2 is going to be 6. But what we need to do here is to reduce that remainder by 5. So when we have a remainder of 6, we take 5 away to be 1. So if it's bigger than 5, we take away 5. So if it's 6, then we take away 5, which is 1. So the Q3 needs to go to Q1 on 0, and the next one in the line is going to be Q2, which is, so that's where the 1 goes. And then Q4, let's see. So Q4, multiply the remainder by 2 is 8, and then reduce by 5 is going to be 3. So then that's going to be here. And then the next one in the line for the 1 is itself. And so that's the entire DFA. So let's actually just check to be sure. So let's do 1, 0, 0, 1, 0. So let's see, so what is this number? So this is the 2's place, 4's, 8, 16. So this is 18 in binary. So this should land us at Q3 because 5 goes into 15, and so 18 has a remainder of 3. And we can see, well, Q0 goes to Q1, then to Q2, then to Q4, then we stay at Q4, then we read a 0 go into Q3. And so how do we do this in general then? So Cn is multiples of n. So what do we do here? So let's do this formally. So then, so let's see. So then we're gonna construct a DFA. I'm gonna call it D sub n because it depends on the n here. So then it's gonna be some set of states, sigma delta Q0F as usual. So Q, the set of states, is going to be the numbers from 0 up to n minus 1. So I'm going to, we can call them Q0 up to Qn minus 1, but I can just leave them as numbers. It doesn't really matter. So then the start state is going to be 0 because that's the state that corresponds to no remainder at all, which means it's a multiple. The set of final states is going to be just 0 and nothing else, the state 0. And then the transition function from a state I, so just some number, reading a 0 is going to be, what is it? So it's going to be 2 times I, because it's multiplying by 2, and then modulo, so take the remainder with respect to n. And then delta of I1 is going to be 2 times I plus 1, that whole thing, modulo n. And I should put parentheses around this too. Okay, cool. So this actually shows that the language Cn is always regular for any n at least 1, because we can always make a DFA for it. And we can prove this. So the basic idea is that we look at the partial strings right here, so the W1 through Wi, and then we can prove by induction that it works in general. And it's actually pretty easy to show, which is kind of like this. So so let's just say we have a W1, W2, W3 up to WS, for example. I'm not going to use n here because the language has n in it. So let's proceed on induction. So if s is equal to 1, well, that's one character. So if W1 equals 0, then we are going to go to the state. Actually, let's make the initial case going to be s equal empty. Okay, I'm not sure what happened here. So let's just close it. Okay, I'm not sure what happened there. So let's actually just look at the empty string. So s equals 0. So the empty string is equal to 0. It represents 0. So we are in the state Q0, which is final by definition. And we want this because 0 is a multiple of any number. So this is good here. So then let's just say that s is equal to k for some k. And then, actually, we want to show it's k plus 1 for some k, and is true for all s less than or equal to k. So it was true up from 1 up to k, and we want to prove the k plus 1 case. So let's look at the string w1, w2 up to wk minus 1, actually I used s here. Actually, let's just do k. And then wk plus 1. And the string from w1 through wk, that is, we've already shown that, for example, by induction, to be the right state. So let's see. Well, either, so let's see. So then w1, let's just say that we're going to let the remainder of the first piece modulo n, this whole thing modulo n equal to p, for example. The remainder is p. Well, let's see. By definition, then the transition function after reading w1 up through wk plus 1 is going to be in state 2p, how was it? So it was 2p modulo n if wk plus 1 is equal to 0, and 2p plus 1 modulo n if wk plus 1 is equal to 1. But that's literally what the definition of putting a 0 on the end of a binary number does, and 1 correspondingly. So they're going to be in the correct states for that reason. So I told you it was pretty easy to prove. Okay, so then therefore the language up here, Cn, is always regular. So I hope that was interesting, and I'll see you in the next one.